Hello everyone. So in the previous class, we discussed about Lebesgue integral of non-negative measurable functions. Let's continue the discussion. Let us see first Fato's lemma. What it says, suppose if you are having a sequence of non-negative measurable functions, say fn, which is converging to f over the set E, then we have to show that integral of f over E is less than or equal to limit inferior of integral fn over E. What is meant by limit inferior? See, you should note that limit inferior is same as the limit of a function, but suppose if you consider a set of all limit points, then the lower bound and upper bound are called limit inferior and limit superior. Now let's see the proof. Without loss of generality, let us assume that the convergence is everywhere. Since the integrals over the set of measure 0 are 0. Because if you consider integral 1 over E, it is nothing but measure of E. And if the measure is 0, then the integral is 0, obviously. And let us consider a function h, which is a bounded measurable functions, which is less than or equal to f, and vanishes outside a set E dash of finite measure. Remember, your E dash is subset of E only. So, if you consider any x outside this E dash, say in E, then their measure is 0. And define a function hn by setting hn of x is minimum of these two. Suppose say h of x is the minimum, and you should note that your h is less than or equal to f, therefore h is bounded, hence hn is also bounded. Suppose minimum is say fn, but fn tends to f, therefore it is bounded, hence hn is always bounded. Say it is bounded by the bound for h, because for fn is also f is bound, and for h is also bound is f, and vanishes outside E dash. That is, if you consider any x belongs to E, for that, if it is not in E dash, then measure will be 0. Then your hn will always go to h for each x belongs to E dash. And we'll apply bounded convergence theorem. What it says, suppose if you are having a sequence, say fn, of non-negative measurable functions, and it is bounded for each x belongs to E, and if limit as n tends to infinity, fn of x is equal to f of x, then integral of f over E is equal to limit as n tends to infinity, integral fn over E dash. We'll apply that theorem for this hn. Then by that theorem, integral h over E is equal to integral, see, remember, because if you classify this into two, if you partition this E into elements which are present in E dash and not in E, then for such integrals, the integral of h over for which the elements which are not in E dash, we knew that it vanishes outside, therefore that integral will become 0. Simply you will get this itself. Therefore these two are equal. And by bounded convergence theorem, this is equal to limit as n tends to infinity integral E dash hn. But remember, your hn is bounded by the bound for h, and it is minimum of h and fn. So you consider all the limits, and obviously because hn is either h or fn depending on the minimality, but each of h is less than or equal to f, and fn is also less than or equal to f. Therefore, it is less than or equal to limit inferior, that is the lower bound of limit of these functions as n tends to infinity integral of fn over E. Now take the supremum on both sides. For this there is no harm, but supremum of this integral h over e, where h is less than or equal to f, by the definition of Lebesgue integrability of non-negative measurable functions, this becomes integral f over e is less than or equal to limit inferior as n tends to infinity integral fn over e, and this completes the proof. Let's see the next theorem. Next one is monodon convergence theorem. What it says, suppose fn is the sequence of increasing non-negative measurable functions and fn converges to f almost everywhere, then we have to show that integral f is same as limit as n tends to integral fn. The proof is very easy because already we have proved by Fatou's lemma that integral f over e is less than or equal to limit inferior n tends to infinity integral fn over e. And you should note that for each n we have fn less than or equal to f. And by the earlier results, if this is less than or equal to f almost everywhere, then this is true. But this implies that limit superior of integral fn, that is the upper bound of the integral of fn's, their limit, that is limit superior of integral of fn, is also less than or equal to f. But integral of f is less than or equal to limit inferior of this. So these two implies that integral of f limit as n tends to infinity integral fn. So this completes the theorem. One where it is less than or equal to, the other one where it is greater than or equal to. This is possible only if the limit is same. So this completes the proof of the monodon convergence theorem. Let's see, I had given problems. You just work it out this and write as assignment. Next definition. A non-negative measurable function is called as integrable over the measurable set E if the integral of f over e is finite. So, at given proposition, if f and g are two non-negative measurable functions and if f is integrable over e, and suppose g of x is less than f of x for each x in e, then show that g is also integrable. It's very simple because we can write integral of f over e as f minus g, integral of f minus g over e plus integral of g over e. And remember, this is finite by the definition of integrability. If this is finite, then the right hand side must be finite. Therefore, if this is also finite, this is also finite. If this is finite, then g is integrable. And this completes the proof. Thank you.